Hey guys, it's Miss Johnson, and I'm here to bring you our notes video for the first part of chapter 1.3, section 1.3 in your book. If you are following along in your book, I'm on page 54, so you can go ahead and turn to page 54 as I talk through some of these notes. Today we're going to talk about measures of center and variability. There's a lot of different ways that we can measure the center of a data set, and there's a couple of different ways that we can also measure its variability or spread, and we're going to talk about how we use those today. They're going to sound like familiar words to you, but we're going to talk about how the different places that we use them and when one is better than the other and how they're affected by outliers and things like that. So the first thing that we want to talk about is the mean. This is our typical standard arithmetic mean. We also use the word x bar. We have the variable x with a bar over the top to note the mean. You can see that right here, okay? And that's just x bar, literally as it looks. So this is when you take the average of a set of data, or in other words, the sum of the data values divided by the number of values there are. We'll record that as this right here, that sum divided by n, okay? X sub I is just marking each data point. X is a data point, and the X sub I tells you that that's the different data points in the data display. So normal arithmetic mean that we've always calculated, add them all up, divide by how many there are. That's something that we've used in many years. So just an example, it says, here's the data on the number of goals scored in 20 games that are played by the 2016 U.S. women's soccer team. They're listed raw there. They're not in order. They're just listed out as the games. So all we did to find the mean is go through and add them up. You can see that as when they were set up in this equation here, they were listed in order. You certainly don't have to do that. We know that adding things in different orders doesn't make a difference. So you don't have to list them in order, but there's a lot of other times that having your data sorted in order is helpful. One of the reasons they did that is because they then turned that data into a dot plot down here. And we're going to use this dot plot throughout the lesson today and talk about it. But they found a mean of 3.15 goals. So that was the mean. They added them up and divided by the 20 and got 3.15 goals. So I want you to pay attention to what you're seeing here. You're seeing this 9 and 10 up here, which is part of our data, but 9 and 10 are very clearly outliers. They're very clearly far away from the pattern of data. And our mean is at 3.5 right now, including the 9 and the 10, okay? So now, what happens if we take those out? If we exclude the games that are possible outliers, or the 9 and the 10, how does that change? So instead, look at this mean formula that we have right here. We have all of the data added up minus the 9 and the 10, and we divide it by 18 because we took 2 data points out. So instead of dividing by 20 games, we're only looking at 18 games. So we're going to divide by 18. Look at how that changed our mean. It changed our mean quite a bit. The old mean was 3.15 goals. Now the new mean is 2.44 goals, okay? So one thing that we want to talk about is calculations or measures of center that are resistant versus non-resistant. So this says a statistical measure is resistant if it isn't sensitive to extreme values. So our extremes here made a big difference in our mean, which means that the mean is not resistant. The mean is not resistant to those outliers. It is going to adjust to the outliers. If we have the outliers in our data set and in our calculations, that's going to change our mean quite a bit. So you can see that here. The mean is sensitive to extreme values, which means it is not a resistant measure of center. We have to be careful when we use the mean, especially if our data is skewed or has outliers in it. That's going to make a big difference. When we get into the median is the midpoint of a distribution when the data is listed in order. We have to have an ordered list. So we talked about median when we talked about the median of a highway. The median of a data set is the same. We're in the middle of the data set, but our data has to be in order. So that's something that is important. So to find the median, arrange the data values from smallest to largest. Then it says if the number n of data values is odd, the median is the middle value. However, if the number n of data sets is even, then the median is the average of the two middle values. So that's just what happens when we, you'd have a list of data, and to find the median, you'd cross off from the ends. Remember doing all of this? We'd just straight up cross off from the ends. Let's say we get down to 2 in the middle. We'd have to take those 2 and divide them by 2 to get whatever your median is. Okay, so that's what they're talking about there. But the median is the middle of an ordered data set. So now let's look at an example here. It says here are the highway fuel economy ratings for a sample of 25 model year 2018 Toyota 4Runners tested by the EPA. So fuel economy ratings for 25 2018 Toyota Runners. Here was the raw data. We've talked about this before. Data, when we get it in statistics, data is raw, it's messy, it's ugly, it's not pretty, it's usually not sorted. We have to, the very act of statistics is taking that raw data and making something meaningful out of it. So the first thing that they did here is they sorted their data. Okay, so now they listed it in order for us, and there's actually a way that your calculator will do that for you, so I'll teach you that someday about how your calculator can sort that data. You're going to become very familiar with your stat button in this class for obvious reason. This class is called statistics, so you're going to use the stat button quite a bit. But the stat button, when you put data in your stat editor, there is a way that you can sort it in your stat editor as well, so that it can do that work for you. So now that I have them sorted, I'm looking at 25 data points. That's my n, which means that my median is going to be, if I take 25 and divide it by 2, I get 12 and a half here. So the median is going to be the 13th data point. And the reason I know that is because I'm going to have 12 data points below it and 12 data points above it, and the 13th data point in the order is the middle. Okay, so that's where that 0.5 comes into play. So if I look for the 13th data point, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and you can even check. So there were 12 data points there, then is there 12 after it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 before it, 12 after it, median's in the middle. Okay, so your median here is 22.4. Okay. So let's take a look and do our own median here. We've got here the games for, we're back at the 20 games of the 2016 women's soccer team. So again, that was our raw data. They took our data and sorted it for us. The 20 games tell me, since it's an even number of data points, that tells me that I'm going to be between 2. So I'm going to be between the 10th and 11th point there, because there's a group of 10 above and a group of 10, or a group of 10 below, a group of 10 above, and I need to be between the 2. If I cross off from the end, the 1 in the 10, then that 1 in the 9, 1 in the 5, 1 in another 5, 1 in another 5, 1 and a 4, 2 and a 3, 2 and 3, 2 and 3, and I'm between these 2. Okay, so that's my median. And again, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. And up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. So you know that this line right here is the true middle. Now in this data set, it's pretty easy to find because 2 plus 2 divided by 2 is just 4 over 2, which is still 2. So your median is still 2. But in a regular data set, that's what you would do. You would take the 2, you'd add them up, and you'd divide by 2 to get that average. All right, so now let's talk about comparing the mean and the median. With the mean, we talked about how the mean is not resistant to extremes, okay? The median, however, is based on positioning. So the fact that median is based on positioning, it's not about what extremes I have. It's about the position of the data. You know, in that number of goals scored, I had 1 all the way up to 9 and then 10. This number might as well have been a 200. My median wouldn't have changed. It's not, the median is going to be resistant. The median is resistant to the extremes. The extremes are not going to make a difference to the position of the median. Now, the extremes make a difference to the mean because the mean is based on a sum of the actual data, not based on the positioning of the data. Since the mean is based on the sum, the change in outliers makes a big difference, okay? So let's just take a look at comparing the two, mean and median on the same graph. So if your graph is skewed left, your mean is going to be below. So the median right here of 19 and the mean right there of 17.97, your mean is less than the median, okay? If your graph is skewed to the right, your mean is going to be above the median, okay? Because again, the mean is not resistant to those extremes. So this was that goals scored thing. Our mean was 3.15. Our median is only 2. Okay, so if I look at the difference between the mean and the median is based on position, mean is based on sum of the actual data. So if I have my outliers in there, that brings my mean up higher than the median. When they're roughly symmetric, then the mean and the median should be very close to each other. So this one had a mean of 22.4 and a median of 22.4. That was the highway fuel economy that we looked at. So when they're roughly symmetric, your mean and your median should be about the same. One thing that I really want you guys to write down, because this is something that helps me remember it. Your mean is going to follow the skew. So I can write that right, skew, not y. So if your data is skewed to the right, your mean is going to be up to the right. If your data is skewed to the left, your mean is going to be down to the left. Median is still going to fall within the bulk of the data. So like most of our data in this graph is up here in these points. The median is going to be in there too, because median is about position. Median's not about the sum. Mean is about the sum, so these low values down here are dragging your mean on down, okay? So that's how I think of it. That's how I remember it. The mean follows the skew. Wherever our skew goes, our mean is going to go with it. And that's just another way of telling you that mean is not resistant. The mean is going to follow wherever those extreme values go. If your skew is going up to the right, your mean is going to go with it. If your skew is going down to the left, your mean is going to go with it. Median will stay with the bulk of the data, wherever that may be, but the mean is going to follow the skew. So then here's just kind of terminology or like an official definition of what I was speaking of on the previous slide, comparing the mean and the median. The effect of skewness and outliers on measures of center. If a distribution of quantitative data is roughly symmetric and has no outliers, the mean and the median will be similar. If the distribution is strongly skewed, the mean will be pulled in the direction of the skewness. So there it is. The mean will be pulled in the direction of the skewness, but the median won't. For a right skewed distribution, we expect the mean to be greater than the median. For a left skewed distribution, we expect the mean to be less than the median. The median, however, is resistant. Median is resistant, okay? Median is resistant to outliers because, again, this is based on position, not actual data. So that's why the median is resistant there. All right, let's talk about variability. So there's a bunch of different ways of thinking of variability. One of them that you're probably familiar with, that you've probably heard before, is the range. The range of a distribution is a value. It's the value of the maximum minus the minimum. So the range of that U.S. women's soccer team goal in its 20 games is 10 minus 1, which is 9 goals. So the range of a data set is a single number. The range is not a resistant measure of variability. It's going to go with the data. If I go back to that extreme value, saying, let's say their greatest number of goals is 200, which obviously is a pretty ridiculous number of goals to score in a soccer game. But just for the element of seeing the point here, let's say their maximum number of goals was 200. That would make my range 199 goals. Do you see how that means it's not resistant? It is going to change based on your extremes. And that's just out of the sheer fact that it's defined by the extremes. The only values you use to calculate the range are the extremes, the maximum and the minimum. So that's why it is not resistant. Okay, now obviously 200 goals is a ridiculous number of goals for a soccer game, so that's not something that would exist, but that's just an illustration of how range is going to be very variable. So now let's talk about standard deviation. Standard deviation is where the standard deviation measures the typical distance, I'm still an eraser here, the typical distance of the values in a distribution from the mean. From the mean. That should tell you something about its resistance, okay? So standard deviation is literally what is the standard amount of deviation from the mean, okay? So the mean is your measure that it's used to calculate, and the standard amount of deviation is like about how far we expect each data point to fall from the mean, okay? So there's a big old formula that we use to calculate the standard deviation, and we will do this probably by hand once or twice, but then you're gonna have your calculator do this for you a bulk of the time, because standard deviation is going to be an important measure that we use quite a bit in this class, and it's going to be the basis on a lot of your analysis. So you're gonna do it on your calculator, but then use that value to make a lot of conclusions, and just do a lot of analysis on your data set. But how you calculate the standard deviation, you have to find the mean first. That's step number one. Then you calculate the deviation from each data point from the mean. So you basically take your data minus the mean. Because the standard deviation is a positive value, it doesn't matter if you're moving to the left or the right. What we're going to do here is we're going to subtract those two and square them. And we're going to do that for every single data point. We subtract the 2 and square, subtract the data minus mean and square it, data minus mean and square it, data minus mean and square it, all the way down the line, and you add those up. The reason we square them is because we all know what happens when you take a negative times a negative. A negative times a negative is a positive. Standard deviation is a positive measure. So I don't want to work with those negatives. I need to work with them in positive form. However, because I am squaring them, I then have to take the square root at the very end. So find my differences, square them, find my differences, square them, find my differences, square them. When I'm done with that, then I divide the whole thing by n minus 1. It says you add all the squared deviations and divide by n minus 1. And then once you're finished, that's when you take that square root so that you undo the squaring that you did. So basically squaring it and then taking the square root at the end is just the act of making everything positive, because we don't want to work with the negative values, because standard deviation is about distance from the mean. And distance can't be measured in a negative value, so we need to make them all positive. So this is what the formula actually looks like. It's the sum of the squared differences from the mean divided by n minus 1, and then taking the square root of that. So again, that's a really kind of complicated formula, if you will. We're going to do it by hand here once, and I want you to follow along with me. Grab your calculator if you have not done so already, but we're going to go ahead and find the standard deviation here by hand. So I've got 11 high school students who were asked how many close friends they have. Here are their responses: 1, 2, 2, 2, 3, 3, 3, 3, 4, 4, and 6. So the first thing that I have to do is find the mean. That's step number 1. So go ahead and grab your calculator and find the mean of that data. 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 3 plus 3 plus 4 plus 4 plus 6. I get a sum of 33 there. So the sum divided by n, I get 33, and I know there's 11, so that means that my mean is 3. Okay, great. So then the next thing that I'm going to do is I'm going to find the differences in my data and add them up. So I'm going to take the sum of my data. I did not write that sigma very well. Sorry. Sum. There we go. Of the differences in my data. So I have data minus mean, and I'm going to square it, plus data minus mean and square it, plus, you're going to need more than one line here, sorry. Data minus mean, square it, plus data minus mean. There's how many twos? 1, 2, 3. So 1, 2, 2 twos, 3 twos. Squared. Okay, now I get into the threes. These ones are easy because these are going to be a bunch of zeros. 3 minus 3 squared plus 3 minus 3 squared plus 3 minus 3 squared. And one more. 3 minus 3 squared. I'm still going. Now I got to do the fours. 4 minus 3 squared plus 4 minus 3 squared. And the last one, 6 minus 3 squared. So again, this is just taking the data minus the mean, value minus mean, and then squaring it. So I'm going to get a -2, a -1, a -1, a -1. These are 0, 0, 0, 0. That's a 1, that's a 1, and that's a 3. When I go through and square all of those, squared, 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 I'm going to end up with -2 squared, which is 4, -1 squared, which is 1, -1 squared, which is 1, -1 squared again, which is 1. The zeros I don't need. 0 squared, 0 squared, 0 squared, 0 squared doesn't make a difference. Then I have 1 squared, which is 1, 1 squared, which is 1, and 3 squared, which is 9. I'm getting there. 4, there's a 10, 11, 12, 13, 14, 15, 16, 17, 18. My sum is 18. Okay, so now my standard deviation, or in other words, S of X, let's keep going here. I've got a sum of the squared data of 18. That's the top. And then I need to divide it by 11 minus 1. So 18 divided by 10, this whole thing is 10 obviously, or this bottom is 10 obviously, is going to give me 1.8. And then when I take the square root, second square root of 1.8, I get 1.3416, or we could just say S of X is approximately 1.34. So that is the typical amount of distance that I would expect to see in this data set. Okay. All right, so that's calculating the standard deviation by hand. Now, typically, oh, there's your further ones. Oh, 1.8 squared close friends, and then you take the square root of it, and 1.34 is your standard deviation. S of X squared is another measurement that we are going to look at. So when I talk about the standard deviation, I'm looking at S of X. That's how I mark standard deviation. That's my variable for that. Standard deviation of whatever your variable is, and we usually are talking about X. The other term that we talk about in variability is what we actually get before we take the square root, and that's going to be the variance. The variance is what the value you have before taking the square root. Okay, so two different measurements there, standard deviation and variance. So measuring variability, some properties of standard deviation. Standard deviation is always greater than or equal to 0. That's because it's a distance. We're talking about distance there. It's the typical distance from the mean, okay? Larger values of standard deviation means that there's greater variation. That should be pretty obvious. Standard deviation is not a resistant measure, and that's because it's based on the mean. The mean is not a resistant measure of center, which means the standard deviation is not going to be a resistant measure of center because it's based on the mean. And then standard deviation is exactly that, variation about the mean, okay? So standard deviation and mean are partners, they're friends. Standard deviation and mean are friends. They go together. That's going to be something for you to remember, because when you start comparing data sets and talking about data sets and analyzing data sets, if you're asked about the mean, that means that you need to look at the standard deviation. Okay. Other measures of central or measures of variability, we can look at things like the interquartile range and the quartiles. The quartiles of the distribution of an ordered set is when you take the distribution and divide it into 4 groups. Think of quarters. Quarters is 4, okay? So if I take that data set and I divide it into 4 groups, then I know that I'm looking at the quartiles. The way I like to think of this is if you were supposed to fold a piece of paper into fourths. If I'm going to fold a piece of paper into fourths, the first thing I'm going to do is fold it in half. When I fold it in half, I find the median, okay? Once after I fold that piece of paper in half, if I want to get it into fourths, I'd fold it in half again. So getting the first quartile is really getting the median of the bottom half. And getting the third quartile, or in other words, like 75%, first quartile is like the 25th percentile. Median, it would be the 50th percentile because that's exactly the halfway mark of our data. So the third quartile would be the median of the top half. Okay, so you can see that over here. The first quartile is the median of the data values that are to the left of the median of the whole list. The third quartile is the median of the data values that are to the right of the median of the whole list. The IQR is that middle range. It's this Q3 right here minus the Q1, okay? So IQR is Q3 minus Q1, or in other words, the middle 50% of the data. If you wanted the middle 50% of the data, you'd be looking at the IQR. Okay, so let's talk about how we would find this. So the travel times for 20 New Yorkers are listed below. We're going to find the IQR of the data set. The first thing, the absolute first thing that I have to do is I have to put my data in order, okay? So I'm going to go through this data set and I'm going to list it in order. I see 5, then I see a 10. Is there anything below that? Nope, 10. Then I see a bunch of 15s, but are there any other teens? Oh, there's another 10. There's a 15, a 15, and a 15, and a 15. 4 15s. All right, so then go ahead and cross off those 15s. I know I looked at them. So 1, 2, 3, 4. Then I need to see what's next. I see a 20 and another 20, so I'm gonna have 2 20s. And then, a third 20. And then I have a 25 and a 30. And then, where am I at here? I crossed off my 30. I've got 2 40s. Oh, I have another 30. So 30 and then 2 40s. And I'm going to run out of room. I always do 45. So that was a 45, not a 45. And then 2 60s. So I'm sorry I ran out of room. I'm going to come down below, which makes it kind of messy, but that's okay. And then a 65 and then an 85. Okay, so there's all my data listed in order. I am going to count my N. Oh, I already know my N. It's 20. Let's just make sure I got everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, good. So now I need to find my median. Since I'm looking at 20 data values, the median is going to be between the 10th and 11th, or again, you can cross off from the ends just like we've done in the past, but I know it's between the 10th and the 11th, so I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, which means my median is right there. If I were going to actually find the median, I would do 20 plus 25 divided by 2, which is going to be 45 over 2, which is 22 and a half. Okay, you weren't specifically asked to find the median. We're actually asked for the IQR here, but that's okay. Just because I'm there, it's easy to find it, and it's a good value to have. Okay, so now let's talk about the quartiles. If I'm doing the lower quartile, that means I want to look at the lower half of the data. So the lower half of the data is that first 10 values that goes from 5 all the way up to 20. And I want the median of that. So this is that piece of paper where you fold it in half once. Now you're going to fold it in half again. So I folded it in half once to get my overall median. Now I'm looking for the median of the bottom half. So my median of the bottom half, since there's 10 values here, is going to be between the 5th and the 6th. So 1, 2, 3, 4, 5, and 6. That is right here. That's my Q1. It would be 15 plus 15 divided by 2, which is 30, divided by 2, which is still 15. Since they're the same value, you know it's just 15. But that's what you would do in any data set. That's my Q1. Now my Q3. Q3 is going to be the median of the top half. So look at the top half here. Again, I'm going to be between the 5th and the 6th value of that piece. So 1, 2, 3, 4, 5, and 6. I'm right there. So my Q3 is going to be 40 plus 45 over 2. That's 95. Sorry, that was a bad equal sign. 95, no, 85. I can add 85 over 2, which is 42 and a half. Okay. So Q3 is 42 and a half, Q1 is 15. Now let's talk about IQR. When I find the IQR, my IQR is going to be the difference of those, the range of my inside quartiles. That's what IQR literally stands for, is the range of my inside quartiles. So 42.5 minus 15. And when I subtract those two in my calculator, 42.5 minus 15 gives me 27 and a half. So here's our interpretation of that. If you look down here at this little line at the bottom, it says the interpretation here is the range of the middle half of the travel times for New Yorkers in this sample is 27 and a half minutes. You can see that they talked about what they're looking at, the range of the middle half, that's that IQR. So that's the measurement they're finding. They put it in context of travel times for New Yorkers. In the sample is 27 and a half, so there's our value. And then they also put the units, minutes. So that's what would be needed if you were asked to list what the IQR was. It's not enough to just say 27 and a half minutes. Everything in this class is going to be about writing out and analyzing and interpreting the value that you find. So writing out this whole interpretation is an important piece. All right, so that's to the end of our notes video for today. Thanks for listening, and I will catch you next time.